Hello everybody. In this lecture, we'll discuss about butterfly effect and delirium cancers. The butterfly effect is called as when you send a pulse and get back the echo will have the information of multiple targets. Each target is represented by a peak in the echo. If there is no target, echo will be a straight line. That means you will not receive any signal in return. When there is an echo, if the echo is moderately small, comparatively small in size, so you will get a very little echo. If the target is very large, like a flight or a big flutter, then you will receive an echo signal which is large in amplitude. So on a scope, if you see, you will get a line like this. Now each peak in this line represents a particular target. Each line represents a particular target. I will show you. Here there is a target, and here it's one more target, one more target, one more target. All these are targets. This is in a single sweep. In the sweep 2, second sweep, we got this kind of signal in which all the signals are having the same, all the peaks are having the same amplitude except at locations where the arrow mark is shown. Here the peak is smaller compared to this peak. This is large. Here also this peak was large and which became smaller. And after fourth scan, this peak, which was very large here, has disappeared, almost disappeared in this case. Here the peak which was moderate has raised, then it slowly decreases and vanished in this fourth scan. Now what do you understand wherever there is these two locations, wherever the amplitude in the echo signal is changing, you can understand that the target may be approaching or maybe it is receding. So by just seeing this each scan in a raster or a scope, the operator has to very keenly observe and understand that where is a movement, which is a tough task. So what we can do, we can pass it through, we can sum it up to understand where a moving target. So when you sum up all these scans, a resultant will be like this, as shown in this figure. Wherever there is multiple changes, then it looks like a butterfly, so we call it as a butterfly diagram. Using this butterfly diagram, you can understand wherever there is a butterfly, you can estimate there is a moving target. Understood? So using these scans, how we can identify moving target. The idea of these delirium cancellers, when you pass this sweep, for example, if this is your current scan result, in the next sweep you will get this. When you subtract this signal, when you subtract this new scan from the previous scan, what will you get? You will get a difference, you will get a straight line except the locations where moving targets are there, where the targets are moved. Only at this location you will get a little peak, and at this location you will get a very little peak. Rest of all will be straight line because both the signals are same in amplitude. Except these two locations, signals have same amplitude, so results a 0. Where there is difference, there results either a positive peak or a negative peak of corresponding amplitude. Now this idea can be implemented in block diagram. You can see this block diagram. Using this block diagram, you can implement this idea to get the only information about only the locations where the target is moving. This is receiving antenna and this is the receiver block diagram. Here what you will get bipolar, because some peaks, as in the previous case, previous slide you might have seen, the peaks have got positive peaks as well as negative peaks also. So both the polarities of the peaks are possible, so this is called as bipolar video. In this bipolar video is given to a subtractor directly. One input is given directly, another input is passed through a delay line canceller whose delay time is equal to 1 by pulse repetition frequency. That means a complete sweep was delayed. One complete sweep was delayed, another one is directly given. That means it is n minus 1 sweep and this is n current sweep. N minus n minus 1, the difference will be a straight line except at the places where there is a moving target. Now these sweeps of output of the subtractor will also have a bipolar. That means two polarities, either positive or negative peaks may be present. That by passing that signal through a full wave rectifier, all the bipolar signals are converted to unipolar, which is easy for a observer to understand. There is a target with the magnitude of the velocity of the target may also be estimated by just seeing the magnitude of the difference or the magnitude of the echo pulse. This is how delay line cancellers helps us to understand the moving targets. These delay line cancellers are of two kinds. One is time domain cancellers and the other one is frequency domain cancellers. If you speak producing the delays in terms of time and you are plotting the waveform with respect to time, then it is called as time domain filters. And if you are talking about all this stuff in terms of frequency, then it is called as frequency domain filters. One advantage of time domain delay line cancellers is that a single network operates at all ranges and does not require a separate filter for each range resolution cell. Whereas in frequency case, you need to have separate filters for separate frequencies, because the time constant of the filter circuit changes from frequency to frequency. So that is the problem. So normally most of the cases we discuss about time domain filters only. These delays were first produced using there were water filled pipes through which the signal which is received will be converted to acoustic signal. That acoustic signal was used to allowed through the water filled pipes. You can see that, you can tell very easily velocity of sound in air is different from the velocity of sound in other medium, example liquid or water. So the signal which was received was first converted to an acoustic signal, that means sound signal. That sound signal were passed through the water filled tubes. These water filled tubes will produce a delay. At the other end of the water filled tube, there was a mic which converts back that sound signal into electrical signal. Then it was given to a subtractor. That was the first case. After water filled, the maintenance was very huge in the case of water filled tubes. Now then the researchers have developed one more system which is called as mercury filled tubes, which is also heavy in maintenance. So we got to another kind of delay line, producing delay lines which are used in the discrete components. So these filter characteristics of the delay line cancellers can be: the main purpose of the delay line canceller is to cancel the DC component of the clutter, which means DC component means wherever the target is stationary. Stationary targets means clouds, buildings, mountains, trees, all these are called as stationary targets are the clutter, which is considered as DC component of the scanned signal, which will be cancelled out and only moving targets will be displayed. Because of its periodic nature, the filter also rejects the energy in the vicinity of the pulse repetition frequency and its harmonics. At the end of the, if a target lies at the end of the pulse repetition frequency, which cannot be seen by this type of filters. See, if you see, the filter response can be characterized by this equation: V1 is equal to k sin 2 pi f dt minus theta naught phi naught. Now, if you plot this, the delayed signal delayed by a time pulse repetition frequency Tp, which is pulse repetition PRF. In time domain it is called as Tp, in frequency domain it is called as PRF. So one complete cycle is delayed and plotted. This is the delayed time version of the filter characteristics. If you subtract these two, you will get V1 minus V2, which is this equation. The resultant of this equation can be shown like this. The signal results as a unipolar sine wave whose magnitude goes to 0 after every half lambda, that is 1 by t, 2 by t, 3 by t, 4 by t, 7, like that. Because of this, if some target lies at a pulse repetition, lies at a velocity of its 1 by t time, then that cannot be seen by this delay line canceller, one-dimensional delay line canceller. So that is the problem of this delay line canceller. The spots where the magnitude of the points where the magnitude of the delay line canceller goes to 0, these points are called as blind speeds. These blind speeds are defined as Fd is equal to the blind speed frequency Fd is equal to n by Tp. See here, the relative target velocities which results in MTI response are called as blind speeds. The relative target velocities which results in 0 MTI response are called as blind speeds. The response of the single delay line canceller will be 0 whenever the argument pi FDTP in the magnitude factor goes to 0, pi, 2 pi, etc. Now, when this is going to be 0, 0, pi, 2 pi, 3 pi, 4 pi, so it can be called as n pi. Now, this again can be written as Fd is equal to n by Tp, which is equal to 1 by Tp is Fp, nFp, 1 Fp, 2 Fp, 3 Fp, where Fp is pulse repetition frequency. Wherever, with all the multiples of this frequency, the response goes to 0. The delay line cancellers not only eliminates the DC component caused by the clutter, but unfortunately it also rejects any moving target whose Doppler frequency happens to be the same as PRF, which can be written as 2Vn by lambda or n by Tp, which we have seen in the previous slide also. Thank you.